I did want to introduce Dr. Craig Kundrot.
Thank you, Mark. And thank you for, a special thanks to you, Mark, and to Ruth from a headquarters perspective, setting this up, to Cheryl, Rebecca, Claudio, and the other members of the nature team, and for all of you to travel and attend here. Before we dive in, for how many people is this their first, like NASA, working with NASA encounter? Okay, very good. This briefing is meant for you in particular. I'm trying to give a light touch because NASA has its own culture and language. You know, for example, when you hear ATP at NASA, it usually does not mean adenosine triphosphate. It means authority to proceed. And we have our, you know, our acronym culture is so rich, we even have a term for it, TLA, 3-letter acronym. So I've tried to strip that out and give you just a high-level orientation to how this fits into the scheme of things, and also try and prime some of the discussion for the spaceflight unique aspects. Okay, so the impetus behind this conference was this central question that we've been thinking about for a while. What does NASA need to know in order to decide how to manage the microbiome of the built environment in future spacecraft? Right now on the ISS, our general strategy is, it's kind of like the radiation ALERA principle, as low as reasonably achievable. For ISS, it's kind of as clean as reasonably achievable. That could be a recipe for a long duration mission in enclosed environment. Could be a recipe for applying selective pressure on organisms that are now going to be hard to eradicate with your standard set of cleaners and or other measures. And if they're not particularly good for the plants or the humans, you might have trouble. So that was kind of the thought process that triggered this question. Now, why are we thinking about it? So let me give you some organizational context. Without showing you a bunch of org charts, I'm just going to take you through a stripped down sort of taxonomy, if you will. Let's see if this is the pointer. Yep. So space biology, the space biology program is really kind of the impetus behind this effort. It's within our division of Space Life Physical Sciences Research and Applications, which has the Human Research Program, which is run out of JSC here. And Judy talked about many elements of the HRP work, which is done here, and it's also done at other centers. Space biology and physical sciences are run from headquarters. We are embedded within headquarters within the Human Exploration and Operations Mission Directorate, where you have other programs, including the currently active ISS program, and also programs for the future spacecraft and missions. Okay, and then that fits within the broader scheme of, in NASA, our top level organizations are called mission directorates. Okay, so basically this is a conference coming originally from a space biology perspective for both the reasons of understanding what's happening possibly in future spacecraft, but also to use it as a mechanism for scientific discovery. And we do have the applications to the Human Research Program and the crew in mind as we're doing this. I'm not going to go over this chart in detail, but our organization, which Mark, we just call SLPSEA. It's not a very pretty sounding acronym, but it rolls off the tongue better than Space, Life, and Physical Sciences Research and Applications. I just want to call attention to the twofold mission, which is just like the journal that Cheryl described. We're about enabling exploration and pioneering scientific discovery. And this area that we're talking about today is an excellent example of a research area that covers both of these. We have the practical applications in mind, but it's also, the spaceflight environment is an opportunity for unique types of stimuli to be applied to living systems and for us to observe their response. So it's like another tool for ferreting out how biological systems work. The analogy I like to think about is back in the 60s when heat shock was applied to Drosophila and we saw chromosomal puffing, you know, and so that very simple variable of temperature really started to tease out the whole, heat shock protein story, which then later in the 70s we learned, oh, these are chaperonins and actually they're constitutively expressed, blah, blah, blah. So in a similar way, spaceflight provides a lot of stimuli that may allow us to ferret out pathways in systems that are otherwise hard to get at. Okay, now we're going to switch to historical context. And this would it could take weeks, but I've just pared it down to 3 threads. Okay, the first thread in blue is about the ISS, which is our premier platform right now. So ISS assembly began over 20 years ago in 98. In the year 2000, human occupation, the crew, first boarded, and it's been continuously occupied since that time. Okay, and in 2011, it was deemed assembly complete. Okay, the configuration has changed a little over that time, and there's been a module added and the like, but essentially it switched from a assembly mode to a full-fledged research mode in 2011. So there's a lot of history that you'll hear about in the next couple days that's space station based. You'll also hear about other platforms like Shuttle and Mir that preceded it. That's just a little ISS orientation for what we have available today. The black bulleted or items in the list have to do with exploration. Back in 2003, when the Columbia broke up over Texas, there was a lot of soul searching that ensued. At that time, NASA was just doing low Earth orbit activity and didn't have really any plans to do anything beyond that. And it was deemed that that was not really aspirational enough. And in 2004, the administration released the Vision for Space Exploration that said, we're going back to the moon and on to Mars. That had very broad support, not just in the executive branch, but in Congress and amongst our international partners. And since that time, 2004, Mars has been our horizon destination. We'll talk about the path to that in just a moment. The 2009 flexible path, I'll show you in a little bit more detail in just a moment. The third thread is, if you're interested in how this fits into our broader research portfolio, you can just Google SLPSEA or NASA Space Biology. But you can also you can Google this decadal survey produced by the National Academies of Science in 2011, which catalyzed the formation of our current configuration in SLPSEA. So there's a broad portfolio of research recommended there, much of which is microbiology related. Okay, so we're going to take a little trip back to the past. It's a useful light level reference point. So in 2009, this flexible report was provided to NASA that defined something called the flexible path. Importantly, the far right is Mars' surface. Okay, so over the last 15 years, there hasn't really been any backtracking on that. Everyone acknowledges that Mars is the horizon destination. However, let's emphasize the flexible and flexible path. You see a lot of intermediate destinations here, starting with the moon, then like Lagrange points in the Earth-Moon or Earth-Sun system, then near-Earth objects, AKA asteroids. Then in terms of Mars, you can do a flyby, just zip around, or do a prolonged orbit before you do a stay on Mars. Then you also have the moon where you have orbit and surface activity. And I like this slide because it was really kind of the first one that kind of laid out the destination options. And one way to think of this is these are all possible stepping stones prior to going to Mars. So you as experimentalists can also view these as potential platforms we have available as we work out what's going on in spaceflight. Because we really want to, our goal is that horizon goal. We want to be able to support what's needed for a Mars mission. All right, so what does a Mars mission look like? Well, we'll stick with 2009, nice, since we're in that flashback mode. This is a very important slide. You'll be tested on this after lunch on Friday, okay? C-mark for special copies, hard copies. It'll be an open book test. Seriously, we're not going to go over this in detail, but the way this is laid out, you have Earth at the bottom and Mars on the top, and the space in between represents deep space. I first want to call your attention to the timeline. This is kind of temporal in nature, going from left to right. This launch right here is the launch of the crew. And landing of the crew is 30 months later. Okay? There are variations to this thing, but this is like the standard model that NASA usually thinks in terms of. So we're talking about a 30-month mission. Prior to that, cargo will go up about 2 years in advance. That can be pre-deployed. Why 2 years? It has to do with orbital mechanics and when you have a launch window to be able to send something to Mars on a low energy trajectory. Low energy means low fuel cost, means you can actually do it. Now circled, so the first point I want to make is it's a 30-month mission. Second is the circled items are the inhabited volumes by the crew, right? So this isn't quite laid out in sequential order, but on this one right here, you have Orion. That's the launch capsule and the landing capsule. So that gets you up into space for the crew and back down to Earth. In between, on your transit to Mars, you'll enjoy a nice cruise in the Mars Transit Vehicle, which by most designs will be roughly the size of a recreational vehicle. And you'll probably be with, the exact number is not certain, but on the order of 4 to 5 of your, best friends, which are almost certainly international, which is, well, okay, could raise some interesting microbiological, aspects actually, really when you think about food and intrinsic microbiomes. Upon arrival at Mars, you'll descend, actually not shown as any specific lander in this picture. The MAV is the ascent vehicle, which you'll need to ride back up once you go down. This orange looking thing is the habitat. And then these two open circles I put in as just placeholders to remind us that we'll probably have rovers and spacesuits, okay? And so conceptually, all of these come together as one closed system. It is not advisable practice to open the door on the ISS to let things air out. We never do that. We do have an airlock that does that in measured amounts, but you'd have to replenish that atmosphere, and that's very costly. So this essentially, for a Mars mission, is going to be a closed system that won't have any mass entering it. Not literally, because like when you're doing the Martian exploration, you'll have airlocks, and so there'll be some Mars atmosphere and maybe dust and stuff that gets into the inhabitable volume. But to a first approximation, it's a closed system. And so from a microbiological perspective, unlike ISS, which between the crew launching and cargo deliveries, roughly speaking, every month, it gets an inoculation of new microbiota. Okay, so the take-home lessons from this for the Mars mission is 30 months and roughly 6 or 7 compartments in a otherwise closed system. Oh, and the dashed one is the cargo vehicle, that pre-deployment. Presumably, some of that cargo is going to be used in the inhabited volume. Like it could be pre-deployed food or medical supplies. So they'll be in contact with that too. All right, getting a little bit more up to date on the NASA mission, and this is just more for your general edification. Doesn't really probably influence your discussions a great deal, but it's interesting to see how in this flexible path things evolve. This is the picture that we used in 2016 to depict our exploration intentions. Emphasis on Mars. Notice the size of Mars in the picture. But I want you now, and the subsequent ones, to notice the picture, the size of the moon depicted here. Okay, so in 2016, we had the journey to Mars. In 2017, we had this picture. It's looming larger. 2018, it looks like this. If you want to fasten your seatbelts and don your crash helmet now, this is a good time, because now the current picture looks like this. Okay, and this is the lunar surface. Okay, so in March, we got direction from the vice president, NASA did, to return humans to the moon, to the surface of the moon, by 2024, the end of 2024. So now in this flexible path, architecture, we are already planning lunar surface activity in the late 2020s. Now that's been moved up. Just as a footnote, Congress has not weighed in on this, so history says you might expect some tweaks to the plan. I'll just put it that way. But right now there's a very keen attention on the return to the surface of the moon. And it's widely recognized that lunar surface activity, even though the physics and chemistry of the lunar surface is quite different than Mars, is an excellent testing ground for equipment, operations, a whole host of things. And from a microbiome perspective, it's a whole new system that will be designed fresh and is an opportunity for further discovery and possibly control/management. Okay, so that's the emphasis on our missions and the moon. Judy just talked a bit about the stressors, the challenges that the crew face. So if you're on that Mars mission, you'll face a number of things: altered gravity fields, radiation effects, hostile closed environment, isolation, confinement, distance from Earth. And within those, microbiome is part of that risk and stressor structure. And I think that will be the emphasis over the next 2 days, rightly so. But there's another component that you should be aware of, and that is called planetary protection. And Lisa Pratt is here. She's our planetary protection officer, which most people do acknowledge as the coolest job title on the planet. Weighty responsibility, so be nice to Lisa. I'm not going to go into detail here, but for those new to NASA, it really has two components that are called forward contamination and back contamination. So on this chart, the first is about back contamination. We don't want to be bringing anything bad back to Earth. That could be exogenous microbiological life or mutated terran life. The other is forward-looking, especially in the search for life on other bodies, especially Mars. We don't want to be bringing unnecessary life to, like Mars in particular, and go search for life just to find that we brought, human-associated microbes with us. Having said that, and not going into details, I called it a closed system, which is, I think, certainly true, most true when you think about the human and the vehicle microbiome, what will enter it. But literally speaking, our systems are not closed, they all leak. Like EVA suits have joints, and those are just impossible to make leak-proof. And so the mental image is from the Peanuts cartoon strip, Pigpen, that as an astronaut is doing their EVA, he or she will be kind of emitting a little cloud of certainly gas, and you might expect some microbial associated material with it. So that's another consideration that won't be the focus over these next 2 days, but that's one that you may need to keep in mind from time to time. Okay, so this is the last content slide, and I want to go over this carefully because there are a lot of things going on in spaceflight that can affect microbial life. The most obvious thing is acceleration, especially when we think about ISS and microgravity and how everything floats. But you have launch and landing loads. Those are very transient, on the order of minutes, but they're there. More importantly, you have on the surfaces. On the moon, it's 1/6 the strength of gravity as Earth, and on Mars, it's 3/8. I didn't list asteroids here, but those are essentially, for practical purposes, zero gravity. Now, microgravity fundamentally does three things. When you change the acceleration, three things change. And in microgravity, to use that as an example, buoyancy-driven convection is eliminated, okay? Turns out there's other forms of convection, like surface tension-driven convection, which is well demonstrated by wine glasses and the evaporation and the surface tension changes, and you can do that experiment tonight at dinner. So there's still some convection in some systems, but now no buoyancy-driven. Sedimentation is eliminated, okay? So what previously would have been a suspended bacterium, for example, will now just stay put. It won't, if it's in air, it'll just, stay put unless there's an air current. If it's in a liquid, it's not going to sediment. And if you're in these partial G environments, with what force it sediments, is that an issue or not? We don't know. But certainly the geometry of microgravity, not sedimenting, is going to be distinct from, sedimenting in a 1G field and coming in contact with a surface. And lastly, hydrostatic pressure is a function of gravity, so in microgravity that's turned off. That's probably not important for microbiology, but I include it for completeness. Okay, so you got several things going on with the acceleration environment. Then you have deep space radiation. This is easily a topic for several days or a week. We won't go into detail here, but in space you're exposed to two types of radiation that you don't usually encounter on the ground. First, from the sun, you have high energy particle events, mostly hydrogen and helium. The good news there is, the bad news is first, we can't really predict when they're going to happen. The good news is they're relatively easy to shield against. So from a human health perspective, it looks like there are good operational workarounds. But the story with galactic cosmic rays is different. It's, to a first approximation, a a constant level of radiation. At a more refined level, it varies by a factor of 2 over the solar cycle. But these guys are impossible to shield against, at least so far. They're basically the nuclei of atoms in the periodic table, ranging from hydrogen up to iron, stripped of their electrons and moving at fractions of the speed of light, okay? So this is the kind of radiation that we don't experience down here. Thank you, planet Earth, to our magnetic field and our atmosphere. But up there, no amount of practical shielding that we know of right now can protect against this. So you've got a different radiation environment that is in play. There's an altered internal atmosphere. So as a practical matter in our spacecraft so far, the crew is respiring, producing carbon dioxide, and we rely on engineering systems to pull it out of the spacecraft. Engineering system costs mass and power and maintenance time, et cetera. And so there's a cost-benefit curve, and the engineering systems do not pull CO2 down to ambient levels. It's like 10 times ambient levels and sometimes higher. That's going to be a feature of probably any spacecraft system in the future unless we have a bioregenerative system that really closes the loop. The environment is high in CO2. That might mean lower pH in some systems, maybe not. Trace contaminants, I mentioned it's essentially a closed system, so when you have off-gassing from materials, those volatiles will stick around in general. Lastly, I don't know, I just listed it because it could be a factor. You don't have natural lighting on your spacecraft, and you have a different spectrum, and so if you have